Hi, my name is Christopher and I am a consultant at the Danish Technological Institute. In this course, we'll be looking at directed energy deposition. In this course, we'll have a look at what is directed energy deposition, what are the pros and cons of the process, what type of design possibilities do we have, and what design guidelines are there. We will then look at the available materials and a few use cases of what we can print. Then we will be looking at the safety aspects, what we need to perform before the printing process, how we can use post-processing to obtain our final parts, what types of quality assurance we can use for our DED manufactured components, and finally a list of links and references. Here we have a look at the 7 main additive manufacturing technologies, in which directed energy deposition is one of the technologies. We can see that it is typically divided into 2 main categories, one which is fused with laser, also called lens or laser engineering net shape, and the other being fused with an electron beam. This is called EBAM, and that is the same as electron beam additive manufacturing. But apart from these 2 processes, we will also be looking into wire arc additive manufacturing, or also called WAM. Looking at the ISO standard, we can see that the material for the DED process is metallic materials. The fusion state are melted. The material feedstock are filament, wire, or powder. The material distribution is using a deposition nozzle. The basic AM principle is that you are selectively depositing your material to a substrate. You can be using an electron beam or a laser beam for your source of fusion, as well as the wire arc melting. The process category is then designated as Directed Energy Deposition, or DED for short. We will now be looking at what Directed Energy Deposition is. The first technology we'll be looking into is the lens technology. The main components in this technology is the laser, which is guided through a set of mirrors. We then have a heated substrate, and finally a powder feeder, which is either coaxial or off-axis. The coaxial setup is shown here to the left, where we have a laser beam that is guided through several mirrors. In this case, only one is shown. It is hitting the substrate, which simultaneously we are blowing powder on top of, together with a shielding gas. To the right, we have a similar system, with the only difference being the off-axis nozzle system. If we look at the process flow, we start out by heating up our substrate. We then start our print, at which we are melting the deposited powder. Our part and/or our nozzle moves, and we deposit the next layer. This process continues until we have our finished print, after which we will be having a cool down of the entire part. If we now take a look at the EBAM technology, we have 4 main components. First being the wire feeder, then the electron gun. We have mirrors guiding the electron gun beam, and then we have a heated substrate. The typical setup of the EBAM system is using an off-axis wire feeder that we see here on the left. That is extruding wire simultaneously as the electron beam is being directed towards the substrate. If you look at the process flow for the EBAM technology, it is very similar to the lens technology. So we start up by heating up our substrate. We then start our print, after which we are melting the deposited wire simultaneously as we print. We move our part and our nozzle, and then the next layer is distributed. We continue to do so until our final part is built and we can finish the print. Finally, we are cooling down the entire part that we have processed. Now we are looking into the final of the 3 technologies, namely WAM. Here we also have 4 main components. It is once again the wire feeder. We have a nozzle. We now have a power source and still a substrate. The setup in a WAM process is built using a wire, which is extruded through a nozzle. The shielding gas is also extruded typically through the nozzle. Both the nozzle and the substrate is connected to a power source. Having the nozzle and the substrate connected to the power source allows for an arc to be created between the nozzle and the substrate. This arc is then melting the wire as we are extruding it through the nozzle on top of our substrate. The process flow for the WAM technology is very similar to the lens and the EBAM technologies. We start with having a print, after which we are applying our current to the nozzle and substrate, with them forming an electric arc between the two, after which we can melt our wire as we are depositing it. Next layer is then distributed, and we continue to do so until we have our finished print, after which we will have to allow for cool down of the finished part. Going forward in this course, we will primarily be looking into the lens technology and the WAM technology, as these are the most used within DED manufacturing. In this slide, we are comparing the two against each other. For both technologies, we have a manufacturer size limit that is typically limited by the gantry or robotic system. For the lens technology, you would typically have higher as-built feature precision. You would also have lower as-built surface roughness, and it is ideal for cladding or repair. You can vary your spot size, and multi-alloy use is easier. The benefits of the WAM process is that you will have higher deposition rates, you will have a high feedstock efficiency, as well as high energy efficiency. It is typically used for larger volumes, and there will be an initial low cost. What we are seeing here is the principle behind the lens process. We are depositing our powder through a nozzle system. Simultaneously, the laser is being applied. Here we have a look at the stationary lens process, where either the part or the deposition nozzle is stationary. Another version of the lens process is the multi-axis manufacture, where you can rotate both the deposition nozzle and the gantry system. A brief look at the EBAM process. We can see that the wire is being extruded through the deposition nozzle. The electron beam is out of view in this process, and we can see how it is melting and depositing the wire as we are building along our weld lines. To the right, we see examples of as-built parts using the EBAM process. Now let's have a look at the WAM process. To the left, we have a close-up of the manufacturing process, where we are depositing our wire through the nozzle. The arc is being formed between the part and the nozzle itself. To the right, we see how we can quickly build a bathtub shape. It is a big part being built in just about 4 hours. Now we will have a look at the pros and cons of the directed energy deposition process. When should I be using DED? Well, usually we will be looking at the requirement tree to determine which technology is the most fitting. But for the DED process, we cannot do that. Instead, we can consider these general guidelines. In general, DED produces rougher parts as compared to laser powder bed fusion. You should be using DED when you want to build big and or fast using metal AM, especially EBAM and WAM is suitable for this. If you want to repair, coat or add material to existing small and large scale metal structures, you can use the lens process. Similarly, the lens process can be used to obtain functionally graded materials. On this slide, we are comparing the material properties of the lens process, the WAM process, and a conventionally annealed bar. The general material properties of three typically used materials, namely 360 nil stainless steel, Inconel 625, and titanium 6 aluminum 4 vanadium, are better when you are using the lens process to manufacture your part as compared to the annealed bar. On the other hand, they are worse when you are using WAM to produce your part as compared to the annealed bar. If we have a look at the industrial lens printers, some of the benefits include higher deposition rates of up to half a kilo an hour for typical materials such as steels, titanium and nickel alloys. This is comparable to an SLM 500, which is processing using 4 700 watt lasers. Another benefit is that you can produce large and heavy parts. You can have a mass range typical from 22 kilos to 3,920. The range of available lasers allow you to deposit material fast. The dimension and weight of a lens printer system is comparable to that of an SLM 500 system, but you can build larger parts. One of the downsides is that the industrial lens printers are typically expensive, with prices starting around $250K US. Another benefit is that we can build large end parts using DED. One example we see here below, where we have a rocket exhaust being made using the lens process. Now we'll have a look at the pros and cons of the EBAM process. One of the benefits is that we can deposit up to 10 kilos an hour. We have low material waste, and we can build very large parts. It is ideal for high-value metals due to no oxidation during processing. Some of the downsides using the EBAM process is that it requires vacuum. You will have a high surface roughness of the as-built parts, which will require post-processing, and in general, post-processing is required to reach the final geometry. Now we'll have a look at the pros and cons of the RAM process. One of the benefits is that we can deposit anywhere from 1 to 10 kilos an hour. We have low material waste, and if it can be welded, it can be used for the RAM process. In theory, any scale is possible and you can set it up anywhere. Some of the disadvantages is that we have only 1 millimeter resolution. It is not a fully automated process, and you will have high surface roughness of as-built parts, which requires post-processing. The outcome of your process is highly dependent on the skill of your operator and programmer, and in general, you will be needing post-processing to reach your final geometry. One of the primary downsides using either the lens process or the RAM process is the rough surface finish. Depending on the roughness scale observed, the surface of these parts are very rough. If waviness is excluded from the analysis, typical RA values for the wire DED process, or WAM, is between 45 and over 200 micron. For powder DED or lens, it is between 15 and 60 micron. This is significantly rougher as compared to laser powder bed fusion parts, where the RA values are typically in the range of 5 to 18 micron. However, the surface can be post-processed to a lower roughness with polishing, blasting, deburring, machining, or similar. If we have a look at the general pros and cons, we can see that some of the benefits are that we will obtain good mechanical properties. It is cheap compared to other metal AM processors, and it is ideal for large static parts with no high resolution requirements. Some of the downsides is the tolerances. We cannot obtain the same tolerances as compared to conventional manufacturing. We also have a highly rough surface finish, and the resolution is poor. Let's have a look at the design possibilities of directed energy deposition. One example is functional parts, where you can build parts with internal channels. What we see here is 3 examples of parts with simple internal channels. You should be aware that you cannot build as complex channels as you can with laser powder bed fusion or binder jetting. Another design possibility is cladding. Here we can apply functional layers to existing parts. This can improve the wear resistance of your parts, and it can be used to repair existing parts and obtain high strength mechanical bonding. One of the benefits is that you can produce functionally graded surfaces, and you can add functional features. This is available using a large selection of materials. Some of the other design possibilities is using embossed features and multi-material geometry additions. Here we see a cone being built using a lattice structure, after which we can add a cone shape to the top of our lattice structure. Another typical use of the lens process is repair and/or tip enhancement. Turbine blades are often exposed to high wear, and you can then repair or even enhance the tip of turbine blades by multi-material grading or adding stronger materials on top. What we see on the right is an example of multi-material grading, where we at the bottom have deposited Inconel 525 and at the top have deposited Inconel 718. You can also have multi-material hybrid manufacturing. The hybrid manufacturing in the same machine setup enables multi-material additive manufacturing using classic subtractive operations which allows for as-we-go post-processing of all functionally important features and phases. What about building a rocket using WAM? On the left, we see a rocket being built one section at a time. And on the right, we can see how we can do this in multiple parts of our processing plant, using these different sections and welding them together in the end to form the entire rocket. But why would you build a rocket using WAM? Well, using traditional methods, you have rigid factories with fixed tooling and high labor costs. You would require more than 100,000 parts, and the build time is more than 2 years. The iteration time is even longer, and you have a very complex supply chain. But using WAM, you can consolidate a lot of your parts, allowing you to build a rocket using below 1,000 parts. Both build time and iteration time is a fraction of the traditional process. Finally, the supply chain is pretty simple. If we have a look at the general design possibilities, for lens, some of the possibilities is a high degree of design freedom. We can create simple channels which have thermal functions. For lens and the cladding process, we can create mechanically bonded functional enhancements. We can use it for repairs, and we can use it for multi-material combinations. Finally, we can create graded properties. For WAM, the primary benefits is that we have free-form manufacture, it is large scale, and it is fast. Next, let's have a look at the design guidelines for directed energy deposition. Generally, we talk about near net shape processing. This means that all of the components being made generally requires a large degree of post-processing. What we see here is an overview of the guidelines for lens and WAM. The table is inspired by similar tables produced by Hobbs. In general, the lens process allows for higher resolution, and it is not in the same need of support as compared to the WAM process. When designing channels, there are some considerations that need to be made. Some of the features that are not possible are perfectly circular channels and square channels. Instead, you can work with teardrop-shaped channels, lemon-shaped channels, diamond-shaped channels, or using angle support structures. In general, the advised maximum overhang angle is 30 degrees. Using multi-axis systems, it is possible to create semi-complex channels. The material is always being deposited parallel to the orientation angle of your part. But as you have a multi-axis system, you can tilt and rotate your part and always deposit the material on top of the part as you're building. By utilizing this function, you can rotate your part as you're building and obtain a complex channel. The reason that we have these design guidelines is to ensure that what we are designing is also what comes out after the printing process. Let's have a look at the available materials for directed energy deposition. This is an overview of the available materials for DED. We see aluminum alloys, iron-based alloys, titanium alloys, tool steels, copper-based alloys, nickel-based alloys, and finally copper-based alloys. Let's take a look at what is being built using directed energy deposition. Long programming and setup times makes the process largely unsuitable for prototyping. However, the large deposition rates makes it suitable for building large components as compared to laser powder bed fusion. The example being showcased here is for building a large part in Inconel 716, where if we build it on a powder bed fusion system and we fill out the entire build platform with components, using only one laser, the build time will be around 240 hours and the total cost would be $16,800. If we, on the other hand, produce the same amount of components using the lens DD process, it would only require 10 hours of build time and cost $3,400. In the following slides, we will have a look at how lens can be used for repairing parts instead of replacing them. Specifically, we will be looking into repairing components in gas turbines. The first example is to look at the Honeywell AGG 1500 turbine engine. This engine has been used in the US M1 Abrams tanks for more than 39 million operating miles. If we have a look at the costs for the typical high wear turbine components, we can see that the savings of using repair with lens against replacing the components is more than 60% for all of the 4 showcased parts. When is it worth the investment? If we have a look at the investment costs, these include everything from the machine itself, the facility, the utility costs, wages, and so on. But if we consider the example from before, we would have savings using repairs of over $14,000. So, if we compare it to a machine price of $250,000 we would need to perform 18 complete repairs to cover the costs of the system itself. Now, more than 10,000 tanks have been built since 1979, and we could assume that a significant amount of these would need repairs. The second example of repairing or replacing is looking at aviation gas turbine blade tips. Turbine blades are high wear components and they are subject to damage from foreign objects. New titanium turbine blades are very expensive. They can cost all the way up to $10,000. Using the lens technology to fix broken edges instead can be performed at a fraction of the cost. Let's have a look at health, safety and environment. Let's start by having a look at the safety equipment. The DED powder grain size is below 150 micron, so the typical personal protective equipment needed includes masks with filters, gloves, and workwear. If we have a look at the safety concerns of lens and WAM printing, powder or wire is not approved for use with food, drink, or medical applications. However, the final parts may be approved for these applications. All powders, and especially titanium powder, is flammable and spontaneously combustible. You should keep the amount of loose powder in the process at a minimum due to this explosion risk. As you are working with hot parts, there's a risk of burns. The parts are also typically live and there could be a buildup of static electricity. This leads to the risk of electrical shock. This is especially a concern with the WAM process. Typically, non-collaborative robots are being used, so you should use area restrictions and shielding when processing. Regarding fire and explosion, you need an ATEX workplace evaluation. This is mandatory in Denmark and must be renewed with production changes or at a minimum every 3rd year. The ATEX workplace evaluation looks into the possibility of explosion when handling powder and other explosion risk materials. We already looked at the printing process in a previous chapter. Now we will have a look at what goes ahead of the printing process and specifically for the WAM process. Some of the aspects of the print job preparation includes toolpath preparation. For multi-axis systems, this requires preparation of both robot and table. You need to consider how you can minimize residual stresses, and it is important that detailed features should be placed facing upwards. You also need to consider the materials that you will be using for your processing, as the process parameters are dependent on the materials. These type of process parameters includes laser power, travel speed, and material deposition rate. Generally, support is less used in DED and WAM as compared to laser powder bed fusion. The multi-axis manufacturing allows for less use of support to create overhanging areas, but when used, it should be easy to remove. Now we will have a look at the typical equipment needed for open DED systems. The picture below shows a WAM setup, but open powder DED setups are essentially similar. What we see on the right is a wire feeding system together with the shielding gas and the power source. The wire is being fed together with the shielding gas through the tubings all the way to the deposition nozzle. The deposition nozzle is then able to be moved around by the robot. We then build our metal part on top of our substrate, which is then located on our positioner, which could be part of a multi-axis system. An exhaust fan is allowing for the removal of excess gases being produced during the manufacturing. Now we will have a look at some of the available post-processing options. The first typical post-processing step is heat treatment. The purpose behind this is to remove residual stresses. And this can also be used to optimize mechanical properties, which can lead to more ductile microstructures and even isotropic microstructures. It can be used for both softening and hardening of the material and also the corrosion resistance. Finally, you can remove porosities by combining it with pressure in the so-called hot isostatic pressure process. Next, we have support removal. Here you will remove parts from the platform by either EDM or bandsaw. Basic tools such as pliers, screwdrivers and hammers are used to remove light support structure. Heavy tools such as column drills can be used to remove strong support structure. Another post-processing step is typically deburring and abrasive blasting. Deburring includes different kinds of grinding chips for different materials to smoothing the outer surface. However, these cannot get into channels or small holes or be applied to sharp corners. Instead, for this, you would be using abrasive blasting. Finally, since most DED manufactured parts are of such poor surface quality, they need machining, especially the wire-based parts. Machining will allow the part to reach the final geometrical tolerances as well as skip typical post-processing steps such as deburring and abrasive blasting. Some of the more special post-processing includes electropolishing for obtaining mirror-like surfaces. Electropolishing essentially works by using your part as an anode and submerging into a polishing electrolyte. The electrolyte attacks the surface, and this allows for metal ions to be extracted throughout the surface. If you have protruding surfaces, there will be a larger surface area at which the electrolyte can attack the surface. By doing so, you will be smoothing out these bumps, and in the end, you have a smoother and more even surface profile. Other special post-processing steps includes abrasive flow machining for internal channels. You are essentially forcing the abrasive media through your channel system, slowly grinding away protruding surface features. Abrasive flow machining is poorly used around bends, and complex channels are poorly processed. Another possibility is physical vapor deposition coatings. This functions by bombarding a sputtering target with argon atoms. The bombardment releases sputtered target atoms on top of your substrate, and that creates a thin film on the top of your part. An almost identical process is chemical vapor deposition, and that can be used as an alternative. Now we will have a look at quality assurance for directed energy deposition. Generally, there is a lack of standards in the field, but for design guidelines, you can use the standard to the left, and for process control guidelines, you can use the 3 standards to the right. For quality control, you can use test samples and artifacts. For tensile samples, we have here shown some WAM parts, which you can then test and obtain the mechanical properties. We can also produce reference artifacts, where we here have shown some examples from laser powder bed fusion. These can be used to obtain the geometric tolerances as well as validating the linear distances. We can also perform inline quality control, where we can extract sensor data directly from the machines. This can be used to determine whether our sensor data is lying within the approved ranges of our system. For instance, we can see that the gas flow speed has been within the acceptable range of 37 to 40 meters per second, and it has been approved by the automatically generated quality report. Finally, we have some links and references for further reading. First, we have some general links for more knowledge about additive manufacturing. And here we have some specific links about directed energy deposition. That brings us to the end of this course. Thank you for watching.